In this video, we are going to talk about rates of change and behavior of graphs. So the first thing that we have to talk about is a definition. So the average rate of change of a function f of x over the closed interval from x of 1 to x of 2 is just going to be the slope between the 2 points x of 1 comma f of x of 1 and x of 2 comma f of x of 2. So the formula for the average rate of change is just going to look like the formula for the slope that you're familiar with from linear functions. So the average rate of change is equal to y2 minus y1 over x2 minus x1. And replacing the y's with the functional notation, we could say that this is equal to f of x of 2 minus f of x of 1 over x of 2 minus x of 1. And again, the reason that this looks so familiar to the slope formula that you know from linear functions is because that this is just the slope of the secant line connecting those 2 points, x of 1 comma f of x of 1 and x of 2 comma f of x of 2. All right, and so let's get into the examples. So in our first example, we want to find the average rate of change of f of x equals minus x squared plus 4 over the interval negative 2 comma 1. And so the first thing that we are going to do is figure out what our y1 and our y2 are supposed to be. So in other words, we are going to find f of negative 2 and f of 1. And then once we have those values, we'll have everything we need to plug them into the average rate of change formula, and we'll be able to figure out what that value is. All right, so for our y1 or our y sub 1, in this context, it's going to be equal to f of negative 2, because our x of 1 here is essentially the left endpoint of this interval. And so f of negative 2 is going to be equal to, well, just using the formula for f, we have minus, and then replacing every instance of the variable x with our desired input, we're going to have minus, and then start parentheses, put a negative 2 for x in there, squared plus 4. And from here, we just want to start simplifying. So negative 2 squared is going to be a positive 4. So we have minus still out in front, and then a positive 4. And then plus 4 still, and adding everything up, well, this is, of course, going to be equal to 0. So y sub 1 is equal to 0. And then we want our y sub 2. This is going to be equal to f of 1. Again, because here our x of 2 is going to be that right endpoint, x equals 1. So f of 1 is going to be equal to minus, in parentheses, throw the 1 in there for x, squared plus 4. So 1 squared is, of course, going to be 1, and then we still have that minus out in front, so we have minus 1 plus 4, which is going to be equal to 3. All right, so according to the average rate of change formula, and I'm just going to abbreviate average rate of change AROC. So AROC is equal to, well, according to the formula, 3 minus 0 over 1 minus a negative 2. So now we just want to simplify from here. So in the numerator, we have 3 minus 0 is just 3. In the denominator, we have 1 minus a negative 2 is going to become a 1 plus 2, which is 3. So we have 3 over 3, which reduces to 1. So the average rate of change of f over the interval from negative 2 to 1 is just going to be 1. All right. Continue with our examples. So in the following examples, we are just going to be finding the average rate of change of the given function over the given interval. And so looking at example I here, we want to find the average rate of change of f of x equals x cubed minus 1 on the interval from 1 to b. So here our right endpoint of our interval isn't an actual number. It's just like an abstract value, which is perfectly fine. So we want to find our y sub 1 and our y sub 2 here. So y sub 1 is going to equal f of x of 1, and here x of 1 is going to be 1. So this is equal to, well, 1 cubed and then minus 1. And then simplifying, well, we just have 1 cubed is 1, so we have 1 minus 1, which is going to be 0. Then we want to find our y sub 2. This is going to equal f of b, which is equal to b cubed minus 1. All right. So now we have everything we need to go ahead and plug it into the average rate of change formula. So AROC is going to be equal to b cubed minus 1 in parentheses for our y sub 2 up in the numerator, and then minus 0 for our y sub 1. And then in the denominator, we just have b minus 1. And so we can rewrite the numerator as just b cubed minus 1 over b minus 1. And we are actually going to use what's called the difference of cubes formula to go ahead and simplify this ratio that we have here for the average rate of change. So b cubed minus 1. So this is a difference of cubes, and we can think of minus 1 as a cube by just thinking of it as, well, minus 1 is the same as minus 1 cubed. So we're really, looking at b cubed minus 1 cubed. And so we have a difference of cubes. And so we can use the difference of cubes formula, which tells us how to factor this cubic here. So this is going to factor as b minus 1 times b squared plus b plus 1. Most of you are probably familiar with the difference of squares factorization formula. And so this is a similar factorization trick. And so using the difference of cubes factorization, well, we've peeled off this factor of b minus 1, which we can cancel out with the b minus 1 in the denominator. So let's do that. And so what we end up with for the average rate of change of f over the interval from 1 to b is b squared plus b plus 1. All All right. Now for example 2. So in example 2, we are trying to find the average rate of change of g of x, which is equal to 2x minus 1, on the interval from 2 to 2 plus h. So here our x of 1 is going to be 2, and our x of 2 is going to be 2 plus h. So let's figure out what our y1 and y2 are supposed to be. So y sub 1 is going to equal, well, g of 2, which is going to be equal to 2, then parentheses, put a 2 in there for x, and then minus 1. So simplifying, we have 2 times 2 is going to be 4 minus 1, which is equal to 3. So that's our y sub 1. For our y sub 2, well, this is going to be equal to g of 2 plus h now. And so this is equal to 2, and then in parentheses, we're going to put 2 plus h in there for x, and then minus 1. Then we want to simplify, so distributing this 2 over both of the terms 2 and h, we have 2 times 2 is 4, and then plus 2h, and we still have our minus 1. And so adding up like terms, we have that y sub 2 is going to equal 3 plus 2h. All right, so we have everything we need to go ahead and plug it into the average rate of change formula. So here, our average rate of change is going to be equal to 3 plus 2h minus 3 in the numerator over 2 plus h minus 2 in the denominator. So now we just want to simplify both the top and the bottom to see what our average rate of change is going to be. And so in the numerator, well, if we drop the parentheses, we are going to have 3 plus 2h minus 3. So combining the like terms, 3 and minus 3, those guys are going to combine to be 0. So we just have a 2h in the numerator now. And then over, so again, dropping the parentheses in the denominator, we can go ahead and add the like terms 2 and negative 2, and those guys are going to cancel out, so we just have an h down there now. So we have 2h over h, and from here we can go ahead and cancel out the h's. So let's do that. And so the average rate of change of g over the given interval is just going to be 2. All right. In our next example, so we have a little bit of a word problem. So it says if Dallas is 110 miles away and it took me 90 minutes to get there, what is the average rate of change of my position? And it also follows up asking us what is another name for the rate of change of our position. Okay, so let's figure out what the average rate of change is going to be. So, well, our x of 1 is going to be time equals 0. So 0 minutes into our drive. Our time unit here is minutes, according to the statement. And then x of 2 is going to be 90 minutes into our drive. And our y sub 1 is going to be our position 0 minutes into our drive. So that's going to be 0 miles. You know, at the very start of our drive, we haven't gone anywhere yet. And then y sub 2 is going to be our position 90 minutes into our drive, which is 110 miles away. So for the average rate of change, well, this is going to be equal to 110 minus 0 over 90 minus 0. Which is equal to, so simplifying the top and the bottom, 110 over 90, which we can reduce to 11 over 9. And if we want, we can write this in decimal. So 11 over 9 is just going to be equal to 1.2 and then just repeating. So 1.2 repeating, which I'm going to indicate with a little horizontal bar over the 2. And using the units we have here, miles per minute. And so here, the average rate of change is just our speed in terms of miles per minute. So I'm going to say the average rate of change, still using our little abbreviation. So the average rate of change is our speed in miles per minute. Right, scrolling down. Okay, so now we are going to talk about behavior of graphs. And before we get into our one example here, we have several definitions to go over. So the first definition that we have is for when a function is increasing or decreasing. So we say a function f of x is increasing on an interval from a to b if its graph rises from left to right throughout the interval from a to b. And the important thing to notice here about this interval is that we have parentheses at both endpoints. So whenever we're talking about the behavior of a graph, like is the function increasing, decreasing, or constant, we are always going to use intervals that have parentheses at both the endpoints. In other words, the open intervals. All right? And similarly, we say that f of x is decreasing on an interval from a to b if its graph falls throughout the interval from a to b. And again, so we have examples of both graphs of increasing functions and decreasing functions. So of course, if we view the graphs of the increasing functions as we view them from left to right, well, they are rising. And one important thing to note here is that yes, the behavior of the graph is closely correlated to the notion of slope. That is, if a function is increasing on an interval from a to b, then it is going to have positive slope at every point at that interval. Though, just because we can talk about the slope of a function at a point, we never talk about the function's behavior at a single point. It's always going to be on these open intervals. And we also have the examples of graphs of functions that are decreasing. And again, if we view them from left to right, well, they are falling. And again, at every point on the graph of a decreasing function, we are going to find that at that point, the function has negative slope. All right, and our next definition is about relative extrema. So we say a point c comma f of c is called a relative maximum if there is an interval I in the domain of f of x such that f of c is greater than or equal to f of x for all x in I. So it's not saying that on the entire domain f of c is the maximum, but if we look close enough, that is, if we select a small enough interval in the domain containing c, then f of c is going to be the greatest value of f for all x in that interval. Similarly, we say that a comma f of a is a relative minimum if there is an interval I in the domain of f of x such that f of a is less than or equal to f of x for all x in I. And we use the term relative extrema in general to describe points that are either relative maxima or relative minima. And so as we can see from our figure here, here is the point c comma f of c. And here is the point a comma f of a. See where I want to squeeze this in. And so we can imagine that this graph extends indefinitely. Maybe I will extend it in the same color. So that f of a is neither the lowest value of f, nor is f of c the greatest value of f. But there is an interval around both a and c such that f of a is the least value of f on that interval, and f of c is going to be the greatest value of f on some interval containing c. So we can imagine like what these intervals might be. Let me change colors again, actually, to like blue. So this could be our interval around A. And this could be our interval around C. Maybe I'll give these intervals a little subscript so we know that one contains A and one contains C. And on I sub A, f of A is going to be the least value of f, and on I sub C, f of C is going to be the greatest value of f. So again, that's what it means to be a relative max and a relative min. They aren't necessarily the absolute max or min, but on some interval, they will be the absolute max and min, but only on that interval, not necessarily the domain. So now let's actually talk about the absolute extremum. So we say that a point c comma f of c is an absolute maximum if f of c is greater than or equal to f of x for all x in the domain of f of x. So now we aren't just talking about, you know, there being like some interval contained in the domain, but we're talking about the entire domain. So we are talking about, you know, the greatest value of f. And we say that a point a comma f of a is an absolute minimum if f of a is less than or equal to f of x for all x in the domain of f of x. And there was a typo in the notes. So in the uploaded notes document, this inequality points in the wrong direction. So I have fixed that here in the filled-in lecture notes, but yeah, just be aware that that inequality is supposed to be reversed in the definition of absolute minimum. And again, we use the term absolute extrema in general to describe points that are either an absolute max or an absolute min. And again, we have a figure. So this time our figure shows some relative extrema. So we can see that in this case, so we have a new function f in its graph. And in this case, we have some relative extrema. We have a relative max here at c sub 2. We have a relative min here at c sub 3. But then we also have our absolute min here at c sub 1 and our absolute max here at b. And one important thing to note is that if the interval on which we are finding absolute extrema is closed, like the closed interval from a to b, meaning brackets at both endpoints, then f of a and f of b are also going to be candidates for being absolute extrema. All right, so let's check out our example. All right, so in this example, we are given a graph of a function below in red, and we are asked to label each absolute and relative extrema and determine the intervals on which it is increasing, decreasing, and constant. All right. Let me go ahead and draw some arrows to indicate that this graph extends indefinitely. Okay, so now I'm just going to have us just mark some points that we see as either high points or low points on the graph. So let's go ahead and do that. Because these are going to be essentially our candidates for the absolute or relative extremums. All right, so let's go ahead and label these points. So over here we have, this is going to be -4. Comma 8. This is going to be the origin, 0, 0. Up here we have 2, 4. Then over here we have 5, 0. And this is going to be -6, 4. All right, so just comparing the y coordinates of our different points. Well, if we look at the point at -4, 8, well, this has the largest y coordinate, and indeed it is the highest point on the graph of our function here. Let's go ahead and label this graph with a name for our function. We'll call it f, very original. So it is the highest point on the graph of f. And so it is going to be the absolute max. As we can see, it's going to be 8 is going to be greater than or equal to f of x for all x in the domain of f. So it's an absolute max. So let's go ahead and say that. All right. Now, if we look at this other high point at 2, 4, So it's not the greatest value of f, as we just discussed. That's going to be 8. But if we look, so we can find an interval containing 2 in the domain of f such that 4 is going to be the greatest value of f for all x in that interval. So we could imagine like what that interval might be. Like this could be our interval I. And on I, f of 2 is greater than or equal to f of x for all x in I. So we have a relative max at 2, 4. Okay. And then if we look at our 2 lowest points that we labeled here, so at the origin and at 5, 0. So looking at the graph of f, 0 is going to be the lowest value of f. So these are both going to be absolute minimums. So absolute mins at 0, 0, and see if we can squeeze it in there, 5, 0. All right, and then finally, let's talk about the point -6, 4. So looking at this point, it is going to be a relative min, and again, we can imagine an interval in the domain of f that contains x equals -6. And we will have on that interval that f of -6 is less than or equal to f of x for all x in that interval. So again, we could imagine what that interval might be. It's like projected down onto our x-axis here. So this could be our interval here. So from, well, maybe we'll have it start here. That way we can nicely say that it's from -7 to -5. And so because of that, we have a relative min at -6, 4. Okay, but we also have other relative extrema, and you might not realize this. So every point contained in these intervals where the function is constant is going to be a relative extrema, both a relative max and a relative min, because at each of these points, so let me say, let's look over here. Let me move the labeling of this, 5, 0. So this is going to be the point 6, 0 now. So if we imagine, for instance, like the interval from 5.5 to say 6.5, well, for all x in that interval, f of 6 is going to be less than or equal to f of x, and it's going to be greater than or equal to f of x. And that's just, again, due to the fact that f becomes constant for x greater than 5. So we technically have relative extrema at x, 0 for all x greater than 5. And similarly, the same can be said for over on the left-hand side of the graph of f, where it again becomes constant. So for x less than -6, we are going to have that f is constant for all x less than -6. So again, we are going to have relative extrema at points of the form x, comma, 4 now for all x less than -6. All right, and now we are finally able to talk about where it's increasing, decreasing, or constant. Let me see if I can manage to find us some vertical space to keep writing in here. All right. Okay, so increasing, decreasing, and I'm going to abbreviate increasing just inc, decreasing just DEC, and constant CONST. Okay, so, and again, when we were talking about the behavior of a graph, we only talked about increasing or decreasing in the definition. So a function is just going to be constant wherever it's not increasing or decreasing. And again, just like with increasing and decreasing, you know, we only talk about a function being constant on open intervals. So looking at our graph here, so let's find where it's increasing first. So we want to view the graph from left to right and see where it's going up. So it appears to be going up here. Let me do some arrows. So it's going up. So this will be an interval where it's increasing. And then if we keep tracing from left to right, well, it's going down again. So that's going to be an interval where it's decreasing. But then continuing to trace to the right of x equals 0, well, the graph starts going up again. So this is going to be another interval where it's increasing. And continuing to trace from left to right, well, the graph doesn't go up anymore. So we found all the intervals where it's increasing. So let's state those guys. So looking at the far left here, it looks like the function started increasing at x equals -6 and kept increasing all the way up until x equals -4. So that's going to be the endpoints of our interval, -6 to -4. And again, we are going to use an open interval. And then it was increasing again from x equals 0 to x equals 2. So we will do a set union symbol, and it'll go from 0 to 2. Do be careful. Just depending on the problem, Lumen might want you to give your intervals for where the function's increasing, decreasing, or constant. In the case that there's more than one, just list it off with a comma instead of the set union symbol. But then there will be problems where it does want you to use the set union symbol. So you just have to pay attention to the instructions of the question. All right, and now for decreasing. So tracing from left to right again. So initially, well, we aren't going up or down, so that's going to be a place where the function's constant. And then we keep tracing from left to right. There's our interval from -6 to -4 where it's increasing, and tracing to the right of x equals -4. Well, again, the graph was going down to the right of -4 as we trace from left to right. So that's going to be an interval where the function's decreasing. All right. And continuing to trace from left to right, well, we know it's increasing from 0 to 2. So let's start tracing from the right of x equals 2. And now as we trace from left to right, well, the graph is going down again. So this is going to be another interval where the function's decreasing. So our intervals for where it's decreasing are going to be from -4 to 0. And 0 to 2 to 5. And since the domain of f is all real numbers from, as we can see from its graph, so it goes from -infinity to infinity for the domain. And because we said that a function is going to be constant wherever it's not increasing or decreasing, that means that excluding the endpoints of these intervals, the function is just going to be constant on the remaining open intervals in the domain. So that's going to be from -infinity to -6 and from 5 to infinity. So -infinity to -6 and from 5 to infinity. And again, we can also see that because as we view the graph on these intervals, it's just going to be flat. And it doesn't even matter the orientation here in which we view it. Of course it does for when we're talking about increasing or decreasing, but in the case of constant, the orientation in which we view our graph doesn't even matter because it won't be going up or down. So that's it for this example, and that's it for average rate of change and behavior of graphs of functions.